So I came up with this presentation for a number of reasons, and I think probably the most, and I think our last speaker talked a lot about reliability, and reliability in the protective relaying world means that the relay does what it's supposed to do in the event of a fault or some type of event that would, activate the relay to give a response. The other half of that is called security. And security means that in the relay world that we're not going to trip when we're not supposed to. So there's two important terms that we have to consider when we talk about protective relaying. So over the past decades, both reliability and the stability of these critical assets has improved with digital technology. I mean, we have, in most all cases, in any new application, moved on from the old electromechanical days to the digital relays. And with digital relays, we don't worry about things like calibration. We don't worry about contacts going bad, or the things that we were concerned about with electromechanical relays. But one of the things that, if you look at statistics that show why relays fail, and we're talking about modern digital relays, the biggest reason is because they're not set properly. And by setting, I'm not talking about just pick up and drop out and time dials of a certain protective element, but also the logic and the configuration of these devices as well. Because the more protective elements you put into a relay package, the more the more chances are that something didn't actually get set properly. And sometimes in the commissioning process, that's hard to find. So I want to kind of focus on transformer protection, because I think this is one of the areas where I see most everybody gets involved if you're into relay testing, or if you're a relay engineer that does settings. We're going to kind of give some examples of where that process can go wrong and how to find it before before something bad happens, like a nuisance trip when you go to energize the relay. So we'll look at two examples. Not all digital relays are the same in terms of how they're set or how they look. They can vary quite a bit, even though they're both doing the same job in protecting our transformer. So we're going to go behind the scenes here a little bit and kind of take a look at the setting and the commissioning process. So if you look at a protective relay, multifunction relay for a transformer, you have three protective zones. One for the internal faults of the transformer itself. Now, this is usually done by certain overcurrent relays, but those that we refer to as phase or ground differential relays. So current going in equals current coming out. We know there's no internal fault in the relay in the transformer itself. The other are through faults, and these are transients that actually go through the transformer, something that's occurring outside the protective zones of the transformer itself. And then we have things that are called abnormal operating conditions, and things that just happen, during the normal operation in a substation that can be a challenge or could damage a transformer. So if we look at the one-line protective diagram, this is the one from Beckwith Electric. You'll see here that you have various instrument transformers. You have CTs on both sides of the transformer to measure current going in and coming out. You've got PTs if you have voltage elements enabled as well, which many of them do, to protect from over voltage conditions and things like volts per hertz. But I always categorize the protective relays in two separate sections: those that are proactive and those which are reactive. And the reason I make this distinction is because if you have a phase differential or a differential relay trip that's protecting the transformer, that means you've already got a problem in the transformer itself, because the current should equal what's going in and coming out. And when there's a fault internal to the transformer, that's where the current's going to flow to, and you'll get this difference in current. Okay. So the other, which are proactive, are those elements which are actually saving the transformer from external conditions, things like volts per hertz that we'll talk about in just a little bit, but something that's going on outside the transformer that could happen to actually damage the relay. And those are proactive type of elements. So what other forms of protection does a transformer have? Well, we have Buchholz relays, we have pressure release valves, we have rapid pressure valves, you know, different types of things that are going on to, you know, fire extinguishing cubicles, things that, you know, if something should happen to the transformer, these items would take the transformer out of service to prevent further damage or catastrophic damage. So here's a one-line diagram from a Schweitzer relay, and there's some things that I want to point out here. And you'll see between the two, they're fairly similar. They're diagrammed out a little bit differently, but the elements are pretty much the same. You have your two sets of CTs, and you have your differential relay monitoring the currents on both sides of the transformer, and then you have some of your voltage and some of your overcurrent relays that are those proactive. But there's some things in a transformer relay that are very, very important to be aware of. First of all, you have a breaker failure element. So if there is a fault and you try to isolate the transformer and the breaker doesn't open, you've got to have some kind of a backup means to isolate the transformer. So that would be breaker failure. Breaker wear monitoring. Okay, Schweitzer relays actually will count the number of times a breaker operates that's servicing the transformer. Event reports, RTD inputs if you want to do thermal measurements, restricted earth fault. SER is sequence of events. So in the event that you do have a fault or a series of faults, it will date and timestamp and give you the values that caused the relay to trip. Loss of potential. Okay, so if you have a VT fuse loss, your voltage elements will become disabled, so it won't nuisance trip, but it will close an alarm. Through fault monitoring, one of the things that's very, very much overlooked when people set protective relays for transformer, and then oscillography. So I'll tell you a little story. I was talking to a gentleman that from a service company, and he was in the field and he was actually commissioning relays on a GSU, a generator step up at a nuclear facility, a very obviously a critical asset in a critical location. And they had backup protection. There were two relays protecting it, as you often see in critical assets. And he got a call in the middle of the night, and one of the relays had tripped on the differential. Okay, so this is not a good thing. So he got in his car, drove out the next morning to the site, and by the time he got there, they had already started to disconnect the main connections to the transformer. They're putting up scaffolding. They got all their test equipment out, and he walked up to the foreman and said, he said, by the way, before you start doing anything, have you looked at the relay and checked the oscillography and the event recorder? And he was kind of dismissive. And he said, yeah, no, go away, young fellow. We got to find out what's wrong with this transformer. Well, what was evident here when he started to look at the fault record, there was no differential trip. The relay had actually nuisance tripped, had an internal error on one of the processors. So it's very important that when you set a relay, you set these types of additional functions and capabilities. So in the event that there is a problem, you have the means to look at things. I mean, when I worked for a relay manufacturer, and whenever there was an event or a trip that occurred, they'd immediately call our tech support, and the first question out of their mouth was, "Did you save the through fault oscillography? Did you save the oscillography in the sequence of events? Could you send it to me?" And if they said, "Well, no, we didn't have either of those two things enabled," well, guess what? There's nothing I can do to really help you decide what it was that happened during that event. So one of the important things that we have to look at when we're setting a transformer differential is how the transformer is connected. And we know that normally between the primary and the secondary windings, you have a 180-degree phase shift, but that can change very easily by by anywhere from 3 to 330 degrees. Because when you're applying the relay has to know the correct vector relationships. And you can see here that these over here on the left-hand side are actually from the Schweitzer instruction manual. On the right-hand side, we see from the Beckwith. And you can see that not all transformer manufacturers diagram these out or call them the exact same thing. So IEC says you've got a Y-connected primary or Y-connected secondary, and there's no phase shift between the two windings. So it's just a simple 180 degrees out. When we start getting into, say, a YD1, you have a Y connected on the primary side, a delta connected on the secondary side with a 30 degrees phase shift. So it's important to really look at your transformer nameplate. And that's one of the points that I want to make out. Pretty much every setting that you're going to put into the relay, including the differential, comes from information on the nameplate itself. And sometimes they can be very difficult to read because not all nameplates look the same or are arranged the same. So if you're a person that's responsible for setting or testing a protective relay, you have to understand what this information is telling you. If you're a person that actually goes out and does testing, maintenance testing or commissioning on a transformer, you have to understand what this nameplate is telling you. Okay, so what information do we look at in the nameplate for setting a differential element? Well, we look at the transformer rating, 100 MVA. We look at the high side voltage. We look at the low side voltage. We look at the vector group, so we know how to compensate for that phase shift. And we use the primary and secondary CT ratios to set the differential relay. And how do we use that information? Well, it's quite simple. Here is the setting for the Beckwith relay. And I used to kind of like Beckwith relays. Their software is very intuitive and it's very easy to set. For instance, if we look at the same YD1 transformer, okay, we've got a VABY, we've got a Y connected primary winding, we've got a delta connected on the secondary, and AB would indicate that we've got an additional 30 degrees phase shift. Okay, now down here, we've set our CT ratios for winding 1 and winding 2. Okay, so with that information, what we can do is actually calculate what our tap setting should be. So for a tap winding 1, okay, and this is important because with the Beckwith relay, you have to do this manually. You have to run this formula because the taps are set manually. Okay, so basically we're going to look at the tap setting will be the MVA rating times 10 to the power of 3. That just gives VA with all of the zeros following it, divided by the square root of 3 of your high side line-to-line voltage in kV times the CT ratio. So if we look at the example here, we've got 100 times 1,000 divided by 1.732, which is the square root of 3, divided by 132 divided by 200, which is our CT ratio, and that gives us a 2.19 tap setting on the primary side. You run the same formula for winding 2, and these will be your tap settings. Now, if we go back to the electromechanical days, this is also similar to taking a BD or an HU relay and moving those tap posts into the right position. And what that does is that makes everything equal in terms of what the relay is seeing. Okay, so the tap settings are very important. Now, we can make quite a few errors here. If we say we invert the CT ratios on the primary and secondary side, you're going to have a problem. If we don't put in the right voltage levels, if we don't put in, the right configuration in terms of how the transformer is connected. Okay, so this is very important to pay attention to. So what we see here in the differential setting, we have a minimum pickup of 0.5 per unit. And I'll explain that when we look at the slopes. Slope setting 1, slope setting 2, and a slope point break. okay, and then a second harmonic restraint and an output that goes to the main trip contact of the relay. So this is all fairly simple and very intuitive. If we look at the Schweitzer, it's a little bit different. Okay. Again, we see the MVA rating. We see how you've got a Y connected primary with a CT ratio of 200 to 1. Okay, and then and then the voltage level, and then we go to winding 2, which is Y connected. Okay, it's got a compensation of 1, which actually equates to 30 degrees, a CT ratio of 500, and the secondary winding voltages as well. So we will say that we enabled this element. And the thing about the Schweitzer is once you put this information in, okay, your tap settings will automatically be configured. Okay, and that's the big difference between the two. Now, most all of your modern digital relays for transformers has this auto tap calculation. Okay, but just one little mistake in the information over here on the left-hand side will change these values, and that will give you bad settings. So this is it's simple if you take your time, and that's the big thing. You can't be in a rush. The other problem that I run into is you have two groups of people. You have protection engineers that are actually putting the settings into the relay, and you've got a substation crew that's actually going out and testing and validating those settings in the relay. So if you're testing it, you have to actually rely heavily on the fact that the engineer put those into the relay properly or properly configured the file that you're going to upload to the relay with these settings in there. So that's, you have to understand that relay testing people, whether you're an engineer or a relay technician, you have to have as much knowledge as you possibly can because you're the last line of defense to make sure that thing's going to work. Trip logic, okay, is very, very important, especially with the Schweitzer. Now, with the Beckwith, it was easy. We just checked a box. It said, go to output 1. With a Schweitzer, you have to, yes, say it's going out to a certain protective function, but it has to be part of the trip logic equation. And this can be a little bit complex. You can actually enable the element, but forget to output it to a contact, whether it's an alarm or an alarm and a trip or just a trip. So it's important to make sure that these are doing properly. Now let's talk about the dual slope setting that you see on the differential. Now, a lot of people would ask me that aren't familiar with differential protection, why can't you just put a set of overcurrent relays? Well, you could, okay, but that would be just a one static setting, and it wouldn't account for things like CT CT errors. Okay, protection class CTs are only good up to 10%. So if it's not right on the money, okay, with just overcurrent relays, you're going to have a nuisance trip, and that's why we apply what we call a restraint slope, okay, to the settings. And slope 2, you'll notice that slope 1 is at one level, slope 2 is at another, and slope 2 is there to increase the restraint of the differential element. Okay, so that if you get a through fault from a transient and it causes the CTs to start to saturate, that will add additional restraint to decrease the sensitivity of the SEL-7 element so it won't misoperate. And it looks like this. So this is your restraining region right here, and this is your first 25% slope, and here's where it goes to the second slope, which is 60%. Okay, so this is going to keep your differential relay from nuisance tripping if you have CT saturation or the CTs just aren't that accurate. But once that differential is high enough to indicate that you have a problem internal to the transformer, this is going to be your trip zone up in this region right here. Now, let's talk a little bit about second and fourth harmonic restraint and harmonic blocking. One of the phenomena that happens when you energize a transformer is that you're pushing current into the transformer, but it's not coming out yet. So if you don't block the 87 element from tripping one way or another, it's going to nuisance trip as soon as you energize that transformer. So to keep from that happening, they set a what's called a harmonic restraint. And what happens when you energize a transformer is you have a certain amount of harmonics, let's say 20-25% harmonic component of that waveform in both the second and the fourth harmonic restraint. Now, we use these words restraint and blocking you know, kind of like the same thing, but it really isn't, because if you're blocking the element totally, okay, what's going to happen is that if you actually close in or energize a transformer and there's already a fault that exists, okay, you're going to create an even bigger problem because you're energizing a transformer that's got a fault in it. Okay, so restraint means what we're going to do is we're just going to move the restraint slope up higher and desensitize it if we see a certain amount of second and fourth harmonic in that initial waveform. And this is what it looks like right here. This one was set at 20%. And you'll see that if we have greater than 20% harmonic component, this is your restraint region. If it's less than 20%, okay, that means that you're just operating under normal circumstances. You have a fault in the transformer, and the 87 element is going to trip. Now, there's a couple of things that you have to be careful of, especially with new transformers, because traditionally what you'll see is that whether you had a BDD relay or an HU relay or the old electromechanicals, they were kind of set statically at 20% or 25%. Okay, because that's normally what you'd see in transformers. Well, what we find that new transformers use a high flux density core materials, and that results in lower levels of second harmonic current during the energization. So that makes your harmonic restraint setting less effective. You have ultrasaturation, which is a phenomenon where the core is deeply saturated during the inrush, and that can lead to also very low harmonic content. And that means basically what we're seeing here is that with the new materials in some of your core and shell form transformers are actually giving off a much lower harmonics. And the reason I bring this up is because what that means is that your traditional setting of 25% isn't going to be applicable anymore. You may have to go all the way down to 8 or 10 or 12%. How do you know what kind of harmonics you're going to see? Well, the best way is to energize the transformer and then capture the waveform and analyze the waveform to see exactly how much harmonics is being generated during that inrush. And that will help you with your setting. Otherwise, if you just put it at 20%, you may see a nuisance trip. Now, there's a bunch of different ways to set a harmonic restraint. It's per phase, and that, and in that case, the relay performs a restraint on any of the three phases. 2 out of 3 means that it must restrain if it sees 2 out of 3 phases. And then some relays will do an averaging. In that averaging mode, the first relay calculates the second harmonic ratio and then applies the inrush threshold to a calculated average. In 1 out of 3 mode, all 3 phases are restrained when a blocking condition exists for only any one phase. So 1 out of 3 mode typically reverts to per phase mode after a short time delay, and that will allow tripping. And basically, it can be done either way, and that's a good an important thing to realize, that these are all settings in the relay, and this right here will help define what those settings mean. And it's always a good idea to refer to your protective relay manual to find out. Now, what common mistakes do we see when we're setting the 87 element? Well, one couple of things you want to look for. Number one is if you're swapping out CT ratios between the windings. Okay, and that's easy to do if you're not carefully looking at that nameplate data. So that's one thing I've seen. The other is not accounting for a delta connected CT. Now, a delta connected CT is sometimes there when you've gone from, let's say, an electromechanical relay to a digital relay. and you don't want to add another CT to the system. So you just have to account for the fact that that's a delta connected CT. Well, what does that do to your calculation for the tap setting? Well, it's going to incorporate that times the square root of 3 formula into the tap setting calculation. So you have to be able to make sure the relay is set to accommodate a delta connected CT. Swapping the voltages between the two windings. Okay, leaving the settings, and I've seen this all the time. People will go in, test a relay, put it in service, energize the transformer, and it immediately trips because they left it with factory settings. And I'll tell you this, 100% of the time, factory settings are not going to equate to the right settings that you need. Okay. And that may be some of the settings, it may be all of the settings. And it could be that you thought that the engineer put the settings in the relay properly, but he didn't, or you may have a file that didn't get that got corrupted when you tried to write that file into the settings program. So that's one of the things. Wrong transformer configuration. If you try and configure a DY11 on a DY1, you're going to have a mismatch in the phase angles, and that's going to cause the differential to trip, to nuisance trip on you. Incorrect MVA ratings used to calculate the tap settings, not setting the correct second and fourth harmonic restraint values accordingly, and making sure they're energized. Incorrect mapping of elements to relay outputs. And this is a big one that you can get into trouble with especially with the Schweitzers, because they're a little bit more complex. You have to make sure, okay, that you map that. Not only do you activate that element, but you map it out to the correct contact as well. And the big one, not enabling your sequence of events or your oscillography for any of the elements, not just for the 87. And that's very, very important. That oscillography is going to help you with your analysis in the event that something happens. Okay, let's talk about testing. The very first thing I do, okay, is I do what's called a sanity check. I'll take my test set, whether you've got a Doble, Omicron, or Manta, or whatever kind. To properly test a differential element, you need 6 phases of current. You can't just do it with 3. If you have 3 phases, the best you're going to do is minimum pickup, and you have to swap your test leads. So make sure you have the right equipment to test these relays. So what you're going to see right here is you're going to see the tap setting value on the primary side, and it's 180 degrees out. And then on your secondary side, the tap settings that are calculated there, and that minus 30 accounts for the DY1. Okay, if you don't have these phase angles properly configured in your test set, the relay is just going to trip no matter what values you put on there. All right, so what do we do here? Well, we want to validate, first of all, that we have the test set wired properly to the relay. And then we want to make sure that it's configured properly. Okay, so basically what you see here in the metering screen, and this comes from the Beckwith relay, and you see the same thing with the metering values from Schweitzer, is that I've got my winding 1 currents, my winding 2 currents, okay, and what I'm looking for to make sure everything's wired properly is all positive sequence currents on both the primary and the secondary winding. Okay, and you'll notice that I apply these values. I'm not tripping the relay. I don't get any outputs activated. Well, that's good, because that's not what you want to that's what you want to have happen. This is like just a simple basic wiring check, the sanity check, I call it, to make sure that everything's wired properly. Now, let's say if I've rolled phase A and B on the secondary winding. Okay, let's say that I just put my test leads on the wrong phases. What you're going to see here is we go from positive sequence to negative sequence values. Okay, so that would indicate that I've got the test set wired improperly. And also what you're going to see is you're going to see the relay pickup. So you see that now these pickups are activated. I would say most definitely that this will cause your differential to trip. Because remember, the differential not only operates on the current values that it's seeing, but it's also looking at the phase angle as well. So if your relay is configured wrong or your wiring's wrong, that 87 is going to nuisance trip on you. Okay, so what do we do next to test the element? Well, the next thing is going to be we're going to check the minimum pickup. And remember, our minimum pickup settings was 0.5. Okay, now that's not 0.5 amps. That's 0.5 per unit, okay, of differential. So what that means is if tap winding 1 is at 2.187 amps times 0.5, our minimum pickup should be 1.09 amps. So we're going to put the secondary windings at 0 and just ramp up our current until the relay trips, and that's exactly what it should trip at. Okay, that's the minimum pickup. And we do the same thing on winding 2. And this is no different than we did on our BDD or in our HU. Okay, it's just that it's 3-phase, not single phase. So you have to make sure you ramp all 3 phases simultaneously as you're doing this minimum pickup test. So that will verify the minimum pickup. Now, to verify, okay, the slope setting, okay, basically we can go to our metering screen right here, which is really nice on the Beckwith relay, and they have the same, I believe, in the Schweitzer, and just start to increase one of the phases until we get to this intersection right here and see the relay trip. So it'll plot it right on this line. Okay, so we want to check the slope, both the 25% and the 60% slope, to make sure, and then you can calculate the delta between the 2 windings to validate that the slope is set properly. Okay, so how do we verify our 20% harmonic? Now this is kind of tricky because we have to do 1 winding at a time. What we do is we superimpose frequencies of all 3 phases. So we're going to move our 3-phase test leads from winding 2 to winding 1. We're going to leave the actual, so now we've got 2 sets of test leads going to winding 1. So if it's set at 20%, okay, what we're going to do is we're checking for we're going to look at our second harmonic. So a second harmonic would mean that we're going to have in this test lead 120 hertz. Fourth would be 240. Okay, so a second harmonic component is 120 hertz. So we set this set of test leads to 120 hertz, and we start to ramp it up. Okay, and at 20%, 4.37, okay, which is our tap setting for winding 1, it should drop out at 0.874 amps. Okay, so if we start with 0 right here, it's not seeing any harmonics, it's going to trip. So we're going to ramp up this current in milliamps until it drops out, and it should drop out. That means we have a second harmonic component greater, okay, than 20%, and that will keep the differential from operating. And you do the same thing for if you have a fourth harmonic restraint enabled as well. Second is usually primarily what they use. Adding the fourth harmonic restraint just adds a little bit more security to the restraint on that element itself. Now, one thing I want to talk about is volts per hertz or overexcitation protection, and I think this is one that gets misunderstood very easily. Okay, volts per hertz is a relationship of voltage to current. Okay, it's not a voltage element, it's not a frequency element, it's a combination of both. So generally where we see this enables is on a generator. Okay, but not always. Okay, it could be on a EHV or a high voltage substation. You could have volts per hertz energized as well, and I'll get into that in just a second. But basically, it's looking at the difference and the difference between the percentage difference between the voltage and the current. So in this setting right here, what we have is we have a pickup of 110%. So if our voltage and frequency has a difference of 10%, okay, or 10%, after 360 cycles, it's going to trip. Okay, so what causes this? Well, overexcitation is different from overvoltage because overall voltage protection reacts to dielectric limits, okay? And this could be due to lightning strikes or overhead transmission lines, circuit breaker switching operations, anywhere where your voltage is going to spike. That's going to create a problem in the insulating system of the transformer and actually put a hole in the insulation. But overexcitation is different. It's protecting against what we call overfluxing. Okay, tough word to say. Be careful how you say it. But overfluxing basically causes heating in the transformer. And the voltage excursion may be less than the prohibited limit dielectric limits, okay, of an overvoltage limit. So the excess current causes excess heating, which will cumulatively damage the asset. And if it's left there long enough, it could actually result in a catastrophic failure. Well, how does this happen? Well, one of the reasons you see this setting, volts per hertz, on a GSU is because it's an event that happens to the generator when it is direct connected to the transformer. And with large generating stations, basically you have your generator, you have the transformer connected to the generator, and then you have your main breaker. Okay, so as basically a volts per hertz condition is a reaction to your AVR or your automatic voltage regulator having some kind of an issue, okay, where it's preventing the overexcitation is growing because the frequency and the voltage aren't coming up to speed concurrently. Okay, one's running away from the other. So this could be a problem. Now, there's an overexcitation limiter in most large generators that prevents the AVR from trying to supply more excitation current than the excitation system can supply. But these systems can fail. I mean, one of the definitions of what protective relays do is that they're there when systems fail. And this is one of the things that happens. Because remember, whatever happens with the generator that's directly connected to the transformer is also happening to the transformer. So if you have a volts per hertz condition or overexcitation in the generator, it's also going to create a problem for the transformer as well. So AVR protection in a generator comes in two forms: loss of field protection, which is for underexcited conditions, okay, because that can be damaging as well, but overexcitation protection for these conditions that we're going to set in the transformer relay itself. Now, one of the things that the points that I want to make is you can have overexcitation conditions in EHV or in a transmission system. Okay, and what would cause that? Well, generator load rejection. Okay, on a large scale electrical equipment failure or a large area line failure and power failure, basically the generating capacity of the generator in the plant exceeds what is being used. Okay, and the power plant at that point is required to reduce the generating capacity to that value, which is corresponding. But since the voltage and frequency fluctuations happen so fast, the power plants may not be able to respond fast enough, and you can have an overexcitation event. Okay, power system islanding. Okay, when you have major system disturbances, uncontrolled separation from the power system could take place, and that'll lead to further network stability. Downstream breaker failure creates a Ferranti effect, and that occurs because of light load or an open circuit at the receiving end. So Ferranti effect is basically due to the charging current in the line that can result in voltage or overexcitation conditions. Capacitors and reactors. Okay, when capacitors are off when they should be on, reactors are on when they should be off, can also create voltage fluctuations and runaway LTCs. Now we think of this, okay, as primarily a overvoltage reaction, not necessarily, and that's true. Your overvoltage protection should keep this from happening. But if at the same time these voltage events happen or these transients happen, and you have frequency fluctuation or a drop in frequency, you're going to have an overexcitation condition. So it's good to have a discussion with your relay engineers to perhaps involve or enable volts per hertz protection, not just for generators GSUs, but also for your transmission line protection as well. So this is kind of what the protection curve looks like. It kind of looks like an overcurrent relay where you have your percentage of volts per hertz and your operating time in minutes. And you can see that you have one for the transformer, you have one for the generator, and then you have your actual relay setting that you're going to apply that will protect both generator and transformer. And one of the things that's important here is that NERC tells us that, yes, we must disconnect. Okay, we want to protect our equipment, but they also tell us we want you to stay online if it's just a transient that's not going to damage any equipment. And that's why these inverse time characteristics are applied. We don't want a definite time to say, oops, I see I'm over my volts per hertz rating, I've got to trip immediately. That's not how it's going to work. It's going to see that and then start a timer. And then if it stays around long enough to cause a problem, then it's going to disconnect, because there's a lot of transients that go out on the system that can cause the volts per hertz to react. Okay, but we want to make sure that if it's not going to damage the equipment, we don't want to disconnect. Remember, that's the stability and the security part of what relays do, to not trip when they're not supposed to. So a typical setting, let's say, would be at 1.5% difference between the voltage and the frequency. Okay, it may want to set an alarm so you can just take a look and see what's going on if you have a problem with your AVR system. And then as the volts per hertz value increases, you want to apply you can have either a definite time setting, or you can have that inverse time characteristic as well. But the volts per hertz capability of a step-up transformer connected to the terminals of the generator, have to be considered during the review of this coordination. It's got to be very carefully calculated. And your protective relay manual will help you do this. Now, just a couple of guidelines. For transformer protection for volts per hertz, there was a new IEEE guideline. In fact, I was secretary on this working group, because the old volts per hertz curves were back in the 50s and done by GE, and they haven't been looked at ever since. And what we found was that the new designs on some of the newer transformers had a much higher thermal capability and thermal rating than some of your older transformers. So the curves have been updated in C-57107, and that's a good guide to help you put this setting in properly. But typically the capability of the generator is less than that of the GSU, but not always. Okay, it depends on the age and the type of transformer that you have. And for the GSU, voltage and frequency protection also needs to be coordinated, because you want to make sure that your voltage and frequency elements are properly set, but they should be outside the setting of the volts per hertz element. And also your volts per hertz setting should be greater than 30 cycles. I'd say 30 cycles is probably the minimum to avoid a misoperation. Okay, the other thing is, and this is important, since volts per hertz protection has to protect the transformer and the generator while the generator is coming up to speed, it has to operate at 10 hertz. Okay, so anywhere between 10 and 60 hertz, that has to be enabled, because the voltage and the frequency needs to be proportional as that generator is coming up to speed. And this is what an oscillography would look like in volts per hertz. And you'll see the voltage starting to increase, the frequency starting to come down, and you'll see, this is right when you see the transformer magnetizing current. Okay, so the one thing that I want to point out here, okay, is that a volts per hertz condition can cause the differential element to trip. Okay, and the problem is the volts per hertz condition may not be high enough, okay, to actually trip on overexcitation on that element, but it may be enough to trip the 87 element. So what we see when we have a volts per hertz condition is we see a lot of fifth harmonic component in the waveform of the current. Okay. And this is a good thing to have happen because and I, I, I want to explain the difference between fifth harmonic restraint and volts per hertz protection, because when you have a volts per hertz protection element enabled for the transformer, you also want to enable a fifth harmonic restraint, because you may have enough volts per hertz condition to set off the differential without actually having enough volts per hertz to trip that protective element. So a smallest inclusion of a volts per hertz condition will generate this fifth harmonic. And that's why we need to enable the fifth harmonic restraint, so we don't trip, okay, from just a quick overexcitation event that's not going to do any damage. Okay, so that's the difference between fifth harmonic current and volts per hertz protection. A lot of people get confused as to what the fifth harmonic current is there for, or that fifth harmonic restraint. And that's exactly what it's there for, to keep the differential from tripping should you have a small overexcitation event. So overexcitation can cause the 87 element to trip, and for that purpose, we use fifth harmonic restraint, and we issue a blocking for the differential element as if a single phase fault or two phase fault occurs in the transformer, and one phase remains unfaulted. The differential element's going to remain blocked, okay? Or restraint. I should use that terminology. Okay, so that improves our strategy. Basically, what we do, instead of blocking the whole differential, we're going to just again raise the restraint value. Okay, because let's say what happens. Let's say you have a fifth harmonic blocking going on because of a volts per hertz condition, and at the same time you have a fault internal to the transformer. Okay, so it's a little convoluted, and I don't know if it's ever really happened, but if it did happen, we'll still have some protection in the higher restraint area up here. So common mistakes when testing, and this is really, I think, pretty important, because I've seen this a lot. And I'll give you an example. We were out on again at a nuclear facility, doing a commissioning test on a transformer differential element. And when I went and I went to the nameplate and I configured all I looked at all my settings, or looked at all my test values that I was putting in, the relay was tripping. And I turned to the utility technician and I said, this thing isn't testing correctly. He said, we tested it on the bench. We tested it with everything was fine. And I said, how did you test it? Well, we tested it with the software that we use that takes the settings out of the relay, configures the test, and then applies the right values. I said, okay, well, we better go into the relay and look at the settings. And sure enough, they had rolled the CT values. Okay, so my point is this: if you don't validate the settings in the relay and somebody makes a mistake in putting in the wrong values, the relay is going to fail. Okay, so a couple of common things when you're testing relays that I think are really important. Number one, don't change the settings just for testing purposes, and I saw this on the old electromechanicals. They'd be doing a BDD or an HU relay, and they'd put the tap values on 1 amp or put them on 5 amps and test the slope that way, because nobody wanted to do the math to apply the right per unit values. Well, this happened at Dow Chemical many years ago, and the guy took the HU out of service, moved the taps, tested the relay, put it back into the rack, closed in the CTs, PTs, and trip contacts, and took the substation out of service because he forgot to put the taps back. Okay, so don't go changing your settings. Don't change the logic that will affect the relay's operation when in service. Okay, keep the logic as it will be in service. Keep all your settings and all your logic as it's going to be installed when you're doing your testing. Incorrect wiring of inputs, rolled phase, reverse polarity. I get calls all the time, people doing their distance element. Hey, it's going in the wrong direction. I said, you got a rolled phase. Don't assume that the settings in the relay are valid, either the set points or the logic. Select the appropriate logic for binary IOs. Okay. Make sure if it's a Form A that you're looking at a Form A. If it's a Form B, make sure you're looking at Form B. Not validating that your sequence of events, your target indicators, your fault monitor, your fault or your through fault monitor are set up. If you test them, okay, if you create a fault, go in and look at these different files to make sure you have them set properly. And another one, don't test a relay with factory settings. That just doesn't make sense. Even if you're just doing kind of an assessment test on a new relay that you're thinking on standardizing it, don't test the factory settings. Put real live settings in that would actually apply to where the relay is going to be installed. Okay, there are others. If you can think of others, certainly just let me know. But these are the most common ones that I see during the testing process.